Fine, fine. Thanks. Thank you. So, with these three key points, let us come to one simplest example of frequency domain analysis, which we have already done in your term physics. That is nothing but RLC circuit. So you connected RLC circuit with some values of R and L and C. Then you switched on an input signal, uh, which is of the type sinusoid. Okay. Then you went on varying the input frequency, keeping the amplitude constant. So at particular point, you notice that there was a maximum current flow in the circuit. Okay. So that situation or condition when we encounter maximum flow in the circuit, call it as resonance. Fine. Okay, I repeat, you have done an experiment on RLC circuit, you applied a sinusoidal input, keeping the amplitude or the magnitude of the signal constant, but varied the frequency from say 10 hertz, 20 hertz, 30 hertz, 40 hertz, like that. At particular frequency, we encounter resonance in the circuit, at which there was a maximum current in the circuit. So how you came to know that there is a maximum current? It is one way by connecting a voltmeter across resistance. So whenever you reach a maximum voltage drop across the resistance, it indicates that there is a maximum current in the circuit. So what was the observation made? This is also a kind of frequency analysis. So what was the observation made is that the output is also a sinusoidal type, but with different magnitude than the input and with certain phase shift in the output as compared to that of the input. So these were the key observations made. Okay. So similarly, when you go to this advanced analysis using frequency domain method, we can do the sensitivity to noise or parameter variations. So how does sensitivity to noise can be observed in this RLC circuit? Fine. Suppose imagine you have changed the input frequency, okay, to a very high value, say after range of 25 kilohertz or 30 kilohertz or 50 kilohertz. So when you apply a signal of a particular magnitude to the RLC circuit, whose frequency is very high, then obviously you will end up with some sinusoidal output of the same frequency, but different magnitude and phase angle. Fine. So what I mean to say applying a high frequency is we are experimenting a situation. We're experimenting a situation on the RLC circuit where our input signal of high frequency equivalently represent a noise. Okay, because noise is something like very high frequency signal. Fine. So noise is something like a very high frequency signal, but a practical noise will comprise signals of very different frequencies or high frequency signals which are different one from each other. I mean, if you decompose a noise signal carefully, you may end up with 5 to 10 signals. You may end up with 10 to 50 signals. But the frequency of all those signals will be very, very high. So a similar situation of noise can be experimented by applying a very high frequency input to the RLC circuit. So that's why if you want to know how RLC circuit behaves for a very high frequency signal or a signal which is similar to a noise, your frequency domain analysis will help you for that. Fine. So the story is somewhat different here. Like I said, a practical noise. If you make noise in the class and if you measure it in a mic or record it in a mic and decompose it in using software, all 70 voices will give you 70 different frequencies. Fine. So I am applying that 70 different signals to an RLC circuit. RLC circuit is just a dynamical system for me. So you can have any different dynamical system also. So when I apply a noisy signal of 70 different frequencies, what will be my output? What will be my output? It's difficult to predict at this point of time. Fine. It's difficult to predict at this point of time that when you apply a noisy signal of 70 different frequencies, what will be the output of a dynamic system? Difficult to predict. So why these medical electronics students are making noise? Their classes have started today. I think they are making noise here. Just let me request them. Just wait for a minute. Okay, my question was, if you apply a noisy signal to the dynamic system, to a dynamic system, what will be its output? It's difficult to predict. What I mean, difficult to predict is, let me take your brain as a dynamical system and replace it from RLC circuit. So if I give, say, a signal of a particular frequency, okay, your brain will respond properly. Okay, suppose that particular frequency is coming from only one friend at a time, and your brain can process it very easily and nicely and respond it back. That's the response of your brain. But if at a time 70 people are talking to only one brain at a time, it's difficult to process all 70 signals at a time. So responding is very difficult. Okay. But another approach is like assuming your brain is a linear system. So another approach to find the output for 70 different signals is, you take up or you break or decompose that noise signal which has a 70 different signals. Okay, break up to 70 different signals and process one by one at a time. Process one by one at a time and store the output of individual signals. Okay, assume in a array at the output side. So once you process all 70 different signals at different times, you will get 70 different outputs, and then finally add them up. Then finally add them up. That will give you the response for all 70 signals at a time. Okay, that is called principle of superposition. So that is one, beauty of frequency domain analysis. That is, if you have a signal which is a combination of different signals, you decompose them in a frequency domain and process each and every signal at a time, then add the response for all those individual signals to get the total response. So I hope it is making sense to you. That sort of frequency analysis is meant for, and while doing so, one can easily get a understanding of sensitivity meaning, sensitivity to noise. Okay, your brain of course can withstand the noise up to certain level. So your brain is sensitive only up to certain range of frequencies. So that's what it means. And you can find it. You can find it, and finally you can say my brain is sensitive only up to say this much frequency. Fine. So parameter variation is of course related to satellite. Let me not go into that. It's quite confusing as of now. So I hope everyone is able to understand. So final conclusion is like, if you want to know the behavior of a dynamical system, for a combination of signals is, or for the combination of signals is to break that signal into different frequencies, then process different frequencies through the system at different time, and whatever output you get for each of those decomposed signal, you finally add them up to get the total response. So how do we decompose a given signal into different frequency signals? Which tool we use?
Filters.
Filters. Okay, filters is a different one. Filter will filter only a particular signal from a combination of signal. My question is, how do you decompose a signal into sinusoids?
Fourier transforms.
Okay. Fourier transform or Fourier series, just cross verify it once. Okay. So, but that's Fourier is a main tool. Fine. So next thing is this frequency domain performance is not only related to frequency domain specifications. So from frequency domain analysis, we can extract the information of time domain behavior also. Okay. So I told you to listen as a story. So you just listen it as a story, but parallelly understand that there is a proof for it, which we are not going to do. So the frequency domain analysis, if you do for your dynamical system, you can extract the information of time domain behavior also. Okay. So what exactly frequency domain analysis is? It is a kind of engineering method. It studies the system based on frequency response which is a kind of mathematical model because we are doing with sinusoids and all. So it's a kind of mathematical model. So what is time domain analysis? We can easily define it as it's an approach to find the time domain behavior of a system using some mathematical model, which is nothing but a second order transfer function we had, and then we wrote the expression for C of t for different zeta. Then we wrote the time domain specifications. Fine. So all those things we did using some mathematics. So this is also a similar approach, but now with respect to cos and sine or sinusoidal things. So look at this example now. We have an RC circuit here. We have an RC circuit. And if you derive the transfer function for this RC circuit, what transfer function we will get? So please listen to my explanation carefully. First, before proceeding to frequency response, let me do something with this RC circuit. Let me derive the transfer function of RC circuit. So we know that transfer function is output Laplace by input Laplace. For this RC circuit, the output is nothing but voltage across capacitor, which I have written as X naught of t. Or you can take it as V out of t or V naught of t, anything. And input is Xi of t or Vi of t. So if you take the ratio of Laplace of this X naught of s by Xi of s, you will get the Laplace transform. So before that, let me, please carry a pen and paper. And what is the output of this expression for output across capacitor? Please write it. So what we can do is we can assume a current I here, current I flowing here. So my X naught of t is equal to 1 divided by, what is the expression for voltage across capacitor? Anybody can tell this?
1 by c into integration of I dt.
Yes. 1 by c into integration of I dt. That is X naught of t. So what is X naught of s? The Laplace of that, it is 1 divided by sc, and I dt will become I of s. Okay. So I repeat, X naught of t equal to 1 by c integration of I dt, and X naught of s is equal to 1 divided by c and into s, 1 divided by cs in the denominator, because s 1 by s is introduced because of the integrator. Then integration of I dt, I will become I of s. Next, let me write the expression for Vi of t or Xi of t. So Xi of t equal to R into I of t, the current I flowing here. Then plus 1 by c integration of I dt. Then take the Laplace of this. Xi of s equal to R as it is, I into I of s now. Okay, R into I of s plus again 1 by cs in the denominator into I of s. Now divide X naught of s divided by Xi of s, and what expression do you get at the end? Please check it, whether everyone is getting this transfer function. I and I will get cancelled because it's a common factor both in the numerator and denominator. Anybody got this transfer function for this RC circuit? Small exercise, not a complicated one. See, I have skipped those steps, assuming that you can do it yourself. Since it is just a simple algebra. So X naught of s by Xi of s equal to 1 by cs in the numerator, then R plus 1 by cs in the denominator. So take that cs in the denominator, cs and cs will get cancelled. This is what you will get. Anybody got this transfer function? Abdul?
Yes, sir.
Okay. It's relatively easy, not so difficult. So fine. We can proceed then. So we got the transfer function, and now let us understand what is frequency response with respect to RC circuit. So this is what the input signal I am applying. For the first time, let me say it has a frequency of F1 or omega 1. Okay, F1 hertz or omega 1 radians per second. Omega 1 is nothing but 2 pi F1. We can represent the frequency of the signal both in omega as well as in F. Anything is fine. And let me assume that it has some phase angle with respect to some reference. That I will call it as phi naught. Why I am writing phi naught? You can write it as 0 also. It is starting from origin only, but why you are writing it as a phi naught? Let us write just sine omega t. Maybe a question. But when we do things in a general way, you should incorporate the parameters, all the parameters. Later you can write let phi naught equal to 0 or from observation phi naught equal to 0. That is okay, but you should mention that it has both frequency as well as phase angle. And let me assume the amplitude as A. So I am applying this signal to the RC circuit. Okay. So the usual way of finding the output of this is first take the Laplace of input. Okay. Then write the output. Okay, this has UI input. It is called as UI input. Then calculate the output using our regular procedure, that is output Laplace equal to transfer function into input Laplace. So that's how you can get the behavior. Fine. Where this 1 by Ts plus 1 can be written as transfer function, assuming T equal to RC, time constant. So this was our approach in the previous case, in the time domain case. It is as good as C of S equal to G of S into R of S. That's it. Next, let me show you how do we convert from time domain to frequency domain in this slide. So once you solve that equation, you will end up with two terms. Okay, once you solve for u naught of, okay, uh, once you solve for this u naught of t, by taking Laplace inverse and all, you will end up with two terminologies. So two terms. The first term represents transient behavior, second term represents steady state behavior. Okay. So this transient behavior, everyone knows, it is something like some oscillations, overshoots and all will appear in the transient behavior. And in the steady state, most of the cases it will never have any oscillations. So after certain time, transient response will vanish out because we have e raised to minus t here, and as t increases, this term will go to 0. But we don't have any such exponential minus t term in the steady state part. So this part is nothing but it is going to continue and last for longer time. Fine. Apart from this, we have one more terminology, that is the phase angle. So look into this part later. So as of now, understand, even if you obtain the time domain output for a sinusoidal input, we will end up with two parts like this. Next thing, if you consider only the steady state behavior, leave out the transient part, and if you consider only the transient behavior, this is what you can write. That as limit t tends to infinity, my output is only steady state behavior, okay, which I have replaced and written here, which can also be written as u1m, some magnitude, some constant, into look at the denominators carefully. Look at the denominators carefully. I have written it in a reverse way by adding a j in the denominator part. So this denominator is as good as the magnitude of this expression. Okay, square root of 1 plus omega square t square. Now, where does this angle will appear? angle of this term. Okay, so that is added to the phase angle part. Fine. So what I mean to say is you had applied an input of a sine omega t plus phi naught, but your steady state output is some magnitude which represents the amplitude here into sine omega t and some phase angle which can be obtained from this expression. So the angle for this expression is very well known. It is 1 divided by tan inverse of omega t by 1, or if you take it to the numerator, it is minus tan inverse of omega t. And this is the magnitude. So what one should understand now is, for a sinusoidal input applied, we always get a sinusoidal output, but different magnitude and different phase angle, where phi is also written as this term. Fine. So this is justifiable from the mathematics. So finally what we can write is, when the input to the linear system is sinusoidal, the steady state output is a sinusoidal with the same frequency. Omega t is same for both. Same for both. With the same frequency, but possibly with different amplitude and phase. So this is what I wanted to convey you in this derivation. Fine. So finally what we can write is that if g of j omega, if g of j omega is, if g of j omega is your system, which can be represented in frequency domain. Okay. Now let me skip this part. Let me not confuse. Let me skip that part. I'm not going into that explanation. As of now, you understand, if input is a sinusoidal, output is also a sinusoidal with a different frequency, different phase angle and different amplitude. So if you can catch that part, it is sufficient. Our system is now RC circuit, and it can be any system. It can be RLC, it can be RL, or it can be MBK, or it can be a JBK system. So this is how we can prove it. Fine. So with this, I will stop for today's class. And the key point you should remember is, frequency response is something where we are analyzing the system behavior by applying a sinusoidal signal and measuring its behavior at the output side, which is also a sinusoidal signal but different amplitude and phase. So if you are convinced with that, that is fine for today's class. We can move with the remaining discussion in the next class. So thank you one and all. I'll be ending the class for today.